Maths educational video, Convergence Test. According to definition, this infinite series, summing the entire sequence AK, is convergent if and only if the sequence of partial sums is convergent. And by partial sum, we mean the sum of the first n terms of the sequence. So according to this method, testing convergence of the series is equivalent to testing convergence of the sequence Sn. There's one problem. Partial sums Sn is not easy to find in most cases. We can find Sn only for simple series, such as the geometric series. So we do need methods for testing convergence that do not require the calculations of partial sums. These methods are known as convergence tests. And thanks to the hard work of mathematicians, there's no shortage of such tests. Here's a list of commonly encountered convergence tests. And we're going to discuss the first two in this video. First, we look at the n-term test, which is also known as a divergence test. What the test says is that if the underlying sequence does not converge to 0, which means an is not going to be small enough, then the infinite series will be divergent. Intuitively, this is very obvious, because if you want this series to be convergent, to be a finite real number, then you will expect an to be small eventually. And by small, we mean an should converge to 0. What the n-term test says is that if an does not converge to 0, then the series is divergent. But does it mean that if an converges to 0, then the series must be convergent? It turns out that the answer is no, not necessarily. So we have to be careful not to use this n-term test to conclude convergence. Here's an intuitive explanation. An converging to 0 is not enough because there's this notion of smallness. We want an to be small for the series to be convergent. But how small is small? That's the question. So it turns out that an has to converge to 0 fast enough. For example, 1 over n and 1 over n squared both converge to 0. But obviously 1 over n squared will be much smaller than 1 over n when n is very large. So the behavior of the series for 1 over n and that for 1 over n squared might not be the same. It turns out that the series for 1 over n squared is convergent and the series for 1 over n is actually divergent. And that we'll discuss later. The next test, P-series test. Now this is only applicable to this type of series. You're summing the reciprocal of k power p, k running from 1 to infinity. It's a simple test saying that you have convergence if p is greater than 1, divergent if p is less than or equal to 1. And the explanation for this test is that, like what we mentioned earlier, for the series to be convergent, we want the sequence to be small enough. 1 over k power p will be small when p is large. So when p turns out to be greater than 1, the resulting series is convergent. And that's because 1 over k power p will converge to 0 faster when p is larger. We mentioned these two series, 1 over n squared, in the preceding slide. So it turns out that 1 over n squared being smaller than 1 over n will give us a convergent series, while summation of 1 over k is divergent. And that's because you can think of 1 over k as not small enough to ensure convergence. I end the video with an example on the use of the divergence test or n-term test. We asked to show that this series is divergent. So let's apply the n-term test. All we have to do is to find the limit of this sequence and show that it is not equal to 0. First, we apply a limit law. If you look at this sequence, you know that it is made out of at least two sequences of different nature. The first will be this quantity, which is of the form limit Pn over Qn that we have learned in an earlier video. The other one will be this term, which has to be treated in a separate manner. So we naturally have to split this into two. And for 5 and n, I split them further into two limits. Because 5 power 2 over n and n power 2 over n require the use of different formulas. So essentially we are using the product law. Limit of a n, b, n is the product of the individual limits. And I apply it to three terms. And over here, 2 over n is written as 1 over n squared. And the reason is, we are preparing ourselves for the use of these two formulas, a power 1 over n, which is applicable to this term, with a equals to 5, and then n power 1 over n. And now we apply another limit law, which says that limit of a function of an is the function of the limit. And the function we apply is obviously x squared, because now we have a power 2. So if you look at the preceding slide, we have limit of an, we have limit of an squared. And now we are going to make it limit an to the power of 2. So this is a limit law. And we're going to apply it to the other one as well. Doing so will enable us to apply the formula for the limit of 1 over 5 power 1 over n and limit of 1 over n power 1 over n. As for the first term, we have learned in a previous video that the method requires us to divide the numerator and denominator by the highest power term. In this case, the highest power is simply n power 1. We are now ready to take limits. When we let n go to infinity, these two quantities will both converge to 0. We know that 5 power 1 over n will converge to 1. n power 1 over n will converge to 1 as well, because of these two formulas. And here we are finding limit of a reciprocal. By now we know we can apply the reciprocal limit law, which says that limit of 1 over 5 power 1 over n is just 1 over limit of 5 power 1 over n. So essentially what we get is 2/3 from the first term, 1 over 1 squared from the second, 1 over 1 squared from the third. So finally the answer is 2/3. The limit of the underlying sequence is 2/3. 2/3 is not equal to 0. So the end-term test tells us that this particular series is divergent.